We are in Chapter 1, Section 1, where we are discussing the background to mechanics of materials. We have already done one session, so this is session 2. Here we continue discussing plane trusses. Here again, we have the sessions covered in the first 4 chapters. This gives us an understanding of where we are in the scheme of things, at least for the first 4 chapters. We are now in session 2. Earlier we looked at a plane truss in the last session. This is the truss, and initially we are given the angles at A, D, and B. We assigned the side AC and CB a dimension L, and using geometry we found out the other sides in terms of L. So we found out AD, BP, and CD. We then took equilibrium of the whole truss and found out the reactions RA and RB. In order to solve the truss, we'll look at the joints A, D, and B. We have given a diagram of the whole truss here. Till now, we have found out the ratio of the different sides and the reactions RA and RB. Next, we'll look at the joints. Start with joint A. At joint A, we don't know the force in AC and AD. Here we have the free body diagram of forces acting on joint A. We earlier mentioned that there are two equations, summation Fy is equal to 0 and summation Fx is equal to 0. So here we see that FAC cos 60 plus RA would be 0, from which we'll get FAC. Also FAC sin 60 plus FAD is 0, from which we get FAD. Once we have got the forces, it's helpful to redraw the joint showing the direction of the forces. So since we got FAC as negative, the force is acting towards the joint A. This is the free body diagram of the joint A. So these are forces that act on joint A due to the members and due to the reaction at RA. These are not the forces that joint A itself exerts on the surroundings. Now, this force is due to the member AC. The joint in turn will react with an equal and opposite force. So the force due to the joint on the member AC is shown here. The member AC is in equilibrium, so there would be an equal and opposite force on the other side, which means that the member AC is in compression. Similarly, this force is due to the member AD on the joint. The joint will act with an equal and opposite force at A. So AD being in equilibrium, there will be an equal force here, which means AD is in tension. We have given a diagram of the whole truss here so that we can refer to it as we progress. Initially, we looked at the joint A and we found out the forces in AC and AD. We found out that AD was in tension, so the force of the bar on the joint D would act outwards. In joint D, we now have two unknowns. So we can solve for FBC and FDB. FBC cos 30 is 1000, from which we can get FBC. Once we have got FDC, then FDC cos 60 plus this force would be equal to FDB, from which we can get FDB. So this is the down again. We see that both forces are acting outwards from the joint D. That is the forces we just now found out. That means that the bars DB and the bars CD would be both in tension. So now we have found out the forces in AC, AD, BC, and DB. We need to find out the force in BC. For that, we look at the joint at B, and we need to solve forces only in the vertical direction. So F at BC cos 60 plus this force is equal to 0. We get FBC acting towards the joint B. That means CB is in compression. The forces given here, as shown here, are the forces acting on the joints. They are not the forces acting on the bars. The forces acting on the bars are shown here as well as in the previous slide. We look at another example of a truss. So with this truss, it has a roller support at C, a hinge support at A. It is subject to a load P as shown. Two angles are given, the angle at A and the angle at C. The dimension A is given, and to start with, we need to look at the geometry to find out the relative dimensions in terms of A. Here is another diagram. Initially, we denote the joints. So this is joint D, E, F, G. We see that ED forms a perpendicular with AF, and it also bisects AF. AEF is an isosceles triangle. Also, cos 30 is equal to A divided by AE, which gives AE as 1.155 A. This means that EF is also 1.155 A. Now, BEF is 60 degrees. This angle is also 60 degrees. So then FEG is 60 degrees. Now this angle is 90. So EFG is 60 degrees. That means the angle at G is also 60 degrees, which means that EFG is an equilateral triangle, and EG is 1.155A and FG is 1.155A. Now tan of FBG would be 1.155, from which we can get the angle at B, which we get as 49.1 degrees. Now, if this angle is 49.1 degrees, then this angle is 40.9 degrees. Next, we draw a line parallel to FP from G, which cuts BC at H. Then this triangle GHC is equal to the triangle ABE. Both the sides here are A and the angles are the same. So that means that GC would be 1.155A. Now that we have looked at the geometry, we can find the reactions. Initially, we take moment about A, then RC into this distance, that is AC, is equal to P into A, from which we can get RC. Next, we can resolve forces in the vertical direction. Then we get RAY is equal to P minus RC cos 30. So that will give us RAY. And we also see that RAX is equal to RC cos 60, and this is the direction of RAX. So with the reactions found out, we now look at the joints. So we start with looking at the joint A. Now the forces acting on joint A is FAE and FAD, shown here. So solving force in the vertical direction, we see that FAE cos 60 plus is equal to RAY, from which we can get FAE. And FAE cos 30 plus FAD is equal to RAX, from which we can get FAD. Redrawing the forces on the joint A, we see that FAD acts towards the joint A. Here we have redrawn the truss so that we can keep on referring to it as we progress. Earlier we found out the reaction at C and the reaction at A. We then solved the joint A and found out the forces acting at A due to AE and AD. We found that the force due to AE acts out of A and the force due to AD acts towards A. Now the joint A will react with equal and opposite forces. That means AE will be in tension and AD will be in compression. With AD in compression, at the joint D, there will be a force acting due to AD pointing towards the joint D. Since we know the force due to AD, there are two unknowns at joint D, and we can solve this joint. So here we have the free body diagram of joint D. Using summation Fy is equal to 0, we see that FTE is equal to minus P, and we also find FDF. We have then redrawn joint D with the actual forces. We see that DF is in compression. We now know the force in DE, and earlier we have found the force in AE. So at the joint E, we now have two unknowns. So joint E can be solved. The X and Y axis in joint T has been taken so that resolution of forces becomes easier. The X-axis is along AEG. From summation Fy is equal to 0, we get FEF cos 30 is equal to P cos 30, or FEF is equal to P. From summation Fx is equal to 0, we get P cos 60 minus 1.5P plus FEF cos 60 plus FEG is equal to 0. We have already found out FEF, so we find out FEG. A free body diagram of the joint T is shown here with the actual forces. We see that EF is in tension. We now know the force in DF and we know the force in EF. So at F, there are two unknowns and we can solve the joint F. Using summation Fy is equal to 0, we get FFG plus P cos 60 is equal to 0, from which we get FFG. And using summation Fx is equal to 0, we get FFP. The free body diagram of joint F is given here with the actual forces. Here a diagram of the whole truss is again given, so we can refer to it as we progress. Initially we found out the reaction forces, then we looked at joint A, B, E, and then F. Since we know the force in this member and in this member, we can solve joint G because there are now two unknowns. We consider the X and Y axis, so that solving of the forces becomes easier. So this is considered as the Y axis, and the X axis is along EGC. We earlier solved joint E in the same way. Now this angle is 40.9. Then this line perpendicular to EGC would make a 10.9 degree angle with GB, and FG would make a 30-degree angle. Now solving forces along the dotted line, we get 0.5 P cos 30 is equal to FGB cos 10.9, which gives us the force FGB. Now solving forces in the horizontal direction, we can get the force FGC. So now we have the force in this member and this member. So we don't have the force now only in BC. To find out that force, we consider equilibrium of the joint B. So we know this force and this force cos 40.9, which is the angle here, plus FBC would be equal to 0, from which we get FBC. FBC acts towards the joint. One should note that in this diagram, these arrows show the forces on the joints. So they don't show the forces acting on the bars. These are the forces on the bars. We have looked at two examples on trusses, and we saw that we can start analysis if we have a joint with two unknowns. If we have found the force in a member due to analysis of one joint, then we often move to the other joint of the member if at that stage the joint has two unknowns. We weave through one joint to another based on whether the joint at that stage has two unknowns and is thus ready to be analyzed. At the start or at an intermediate stage, there can be more than one joint with two unknowns. We now look at zero force members. So there are two cases. This is the first case. Here there is no force acting on the joint, and there are two members which are not aligned. So in this truss, at point A there are no forces acting, and AB and AC are not aligned. So the forces in AB and AC will be zero. Here there are three members, two of which are collinear, and there's no force in the joint. Then the third member will have zero force. So in this truss, BD and BA are collinear. There's no force in B, so the force in BC is zero. At joint C, since the force in BC is zero and CA and CE are collinear, force in CD is also zero. Similarly, the force in DE and EF are zero. With any problem, it is advantageous to first look for zero force members. Zero force members can also be cumulative, as we saw here. Next, we look at collinear members. Here, member B and member C are collinear, and the forces acting in the members will be equal and opposite. Also, the force acting in member A would be equal and opposite to this force P. Here we take another example of a truss. Now, this ET is a wall, and a force P is acting on the other end of the truss. To solve this truss, we can start from the right side, and we don't need to find out the reactions at E and D. So initially we need this angle. Tan theta is 60 by 120, from which we find the angle as 26.6 degrees. Now this angle is the same as this angle because this is also 60 and 120. And the angle ECT is twice 26.6 degrees. The angle at B is 90 minus this angle, which we get as 63.4 degrees. Considering equilibrium of joint A, we find out the forces in AB and AC. So AB cos this angle plus B is 0. So we find AB. And once we know AB, then AB cos 26.6 plus FAC is equal to 0, from which we find FAC. Once we have found the force, we have redrawn the joint A. We see that if AP acts towards A, this is the diagram of the whole truss, and we have found these two forces till now. Next, we can look at the joint at B because we already have this force. So here, this force cos 63.4 would give FBC, and this force sine 63.4 plus FPD is equal to 0. So we can get FPD. So now we can look at the joint C because we know this force and this force. Here the summation of forces in the horizontal and the vertical direction gives two simultaneous equations for FCE and FCD. And solving the simultaneous equations, we get FCE and FCD. Find that FCD is 0. At E, the force in EC acts outwards. So there will be a reaction force that is equal and opposite. Now resolving that reaction force in the horizontal direction, we get a horizontal force of 2P. And resolving that force in the vertical direction, we get a force of P. Now here in CD, there's no force. So here also we get a horizontal force of 2P here acting towards the joint. So these 2P forces form a couple. So 2P into 120 is equal to P into 240. The force P here is balanced by the P in this at A. So the whole truss is in equilibrium.